Hey, this is Math 6, Unit 2, Lesson 12, Navigating a Table of Equivalent Ratios. So we started looking at the last lesson at putting equivalent ratios into a table. So moving away a little bit from diagrams and double number lines and just looking at one other way to organize equivalent ratios. So first of all, begin with an activity today, 12.1, number talk, multiplying by a unit fraction. And so this is stuff where they want us to try to do mentally, do some mental math here. And so when you look at 1/3 times 21, a couple things you might pop in your head is something like, I know maybe in my head 7 times 3 is 21. So knowing this in my head, I might recognize that 21 divided by 3 is going to give me 7. Okay? When I look down here, I don't know 6 and 21 any relationship there, but I know that I just did a 1/3 here, and so 1/6 becomes half of that, right? So I multiply 1/3 times a half, I end up with 1/6. So what I'm talking about as a solution for this one is half of 7. So if I knew that was 7, and I go half of 7, I would say 3.5 as a solution there, okay? So just knowing this one allows me to do that one right there. Just some mental math there, okay? On this problem here, we have 5.6 times 1/8. And you might be tempted to change things around, make them both decimals or make them both fractions, but recognize that we have really the number, if you look here without the decimal, 56, right? And so if we know that 8 times 7 is 56, then I recognize there's probably a relationship between 5.6 and the 8 right there. And so in reality, because I know 8 times 7 is 56, and I have a decimal there, if I did 5.6 times 1/8, I'm going to end up with 0.7. Okay, that's because 0.7 is going to be related to those numbers there. So 0.7, they got the 8, 56, we're good to go. Now if you notice that 1/8 then becomes instead of 5.6 times 1/8 is 5.6 times 1/4. Well, a fourth is 2 times larger, right? That's 2 times larger than this one. So if I take this solution and multiply it by 2, I know 7 times 2 is 14, and I have a decimal, I have 1.4. So I don't need to convert all these things and move around. The idea is to find some mental math ways of solving different types of expressions and equations. Okay? All right, let's take a look at the activity for today. Back to our tables and equivalent ratios. Activity number 2 says, we're comparing tacos, says use a table to help you solve these problems, explain or show your reasoning. It says Noah bought 4 tacos and paid $6. Alright, so Noah has 4 tacos. I'm going to put the information here in our table, 4 tacos, and he paid $6. At this rate, how many tacos could he buy for $15? Alright, so there are a couple ways of doing this here, but let's work with the table that we have. What we talked about last time was recognizing, can we find a way to figure out how much maybe one taco might cost? So to do that, to go from 4 to 1, I'm going to multiply by 1 over 4, or divide by 4, same idea, right? So multiply by 1 over 4 would give me 1. If I do that same thing here, times 1/4, to go from there to there, right? That's a times 1/4. Then 6 times 1/4 is 6 over 4, which is the same as 1 and 2/4, which is the same as 1 1/2. But since we're talking about money, that's going to be $1.50. Okay, so there's a little bit of process there to get there, but 6 over 4 is $1.50. So one taco is going to cost $1.50. All right. So knowing that one taco costs $1.50, it says then at this rate, how many tacos could he buy for $15? So if he spent $15, notice that 15 lines up a little bit nicer with $1.50, doesn't it, right? To go from $1.50 to 15 is done by multiplying by 10, isn't it? 10 times $1.50 gets you 15. That's why the mental math exercise was in preparation for this. So we can take our 1 then and multiply it by the same multiplier times 10, and 1 times 10 is 10, which tells me that he'd be able to buy 10 tacos for $15. So rather than just kind of skip to that part, we were able to kind of break it down into one taco per how much, and then use that number that was a little nicer, 1 and $1.50, to get a solution there. Well, are there other ways? Sure, there certainly are other ways, right? But let's keep playing with the table for now. Next it says Jada's family bought 50 tacos for a party and paid $72. Were they the same price as Noah's or not? That's the question. We're wondering, are they the same price? So let's see what Noah buy. If Noah bought 50 tacos at the same rate, we would do one. We could do either one. We could do 1 times 50, or we could do 10 times 5. I prefer 10 times 5 because whatever I do here, I'm going to do here. So let's do 10 times 5, gets me 50, okay? And let's do 15 times 5, just a little bit easier number to work with. 15 times 5 is 5, carry the 2, 75. So when Noah bought tacos, this is Noah's table here, he paid $75 for 50 tacos. Jada paid $72. So Jada's were less expensive than Noah's were. Okay? So we could say that, first of all, we know that Jada's paying $72 for 50 tacos, right? And Noah's paying $75 for 50 tacos. We know that for Noah, he's paying at a rate of $1.50 per taco, right? Do we know what Jada's paying? Do we have any idea there? We're not sure. Could we find that out? Certainly. One way to find that out is to say, well, if she spent $72 for 50 tacos, we take the $72 and we divide it by 50. Okay, I'm going to put my decimal point up right away. 50 goes in 72 one time, so we have 50 there. We subtract and we end up with 22 or 220 by bringing the 0 down. 50 goes into 220 4 times, so that's going to be 200. 200 there, and I'm left with 200 remaining, and so we get that. So we end up with Jada's tacos were costing $1.44 per taco. So Jada's were less expensive than Noah's overall. And we can see that using the table right here. We can find a unit price here, how much for one taco, different ways of going about that. Okay? All right, next one. It says Lynn is paid $90 for 5 hours of work. So use the following table to calculate how much she would be paid at this rate for 8 hours of work. All right, let's see what we have here. So here we have $90 for 5 hours of work. So $90 for 5 hours of work. Awesome. And she's wondering how much does she make for 8 hours of work. So what we can see in the table is we're taking the 5 hours of work and we're converting that into a 1 hour. So this would be how much she makes for 1 hour. We do that by multiplying by the reciprocal or dividing by 5, so times 1/5. 90 times 1/5 got you 18. So we know that she's basically making $18 per hour. And that's what's shown right here in this row. Now we take that and you multiply it by 8, which is shown there, and multiply that by 8, and that says how much money she made in 8 hours. Let's see what the questions are. What is the meaning of the 18 that appears in the table? So the 18 is right here, and it tells me how much money she makes per hour, right? That she makes $18 per 1 hour. Number 2, question here says, why was the number 1/5 used as a multiplier? So right here we saw we went from a 5 in our table to a 1 in our table by multiplying by 1/5. And we did that, why? We did that so that we can find out how much for 1 hour, right? We use the 0.15 to multiply here to go from 5 to 1 in order to get this to a 1 hour to find out what the rate was per hour. So in this case, what Lynn is doing is Lynn is finding a unit rate, right? She's finding a price per hour in order to find out a unit rate to help her solve other problems. Okay? So once she finds that multiplier, she finds unit rate. We say unit rate to find a multiplier. Once she has a multiplier here, which is this part here, then she can use that multiplier. She can add a multiplier to find out any amount she wants. So we look at number 4, because she did the work here to get $18 for 1 hour, because she has that rate, she can now find out how much for 3 hours, how much for 2.1 hours, right? So if it's $18 for 1 hour, for 3 hours, we'd multiply 18 times 3, and we have 4, carry the 2, $54 for 3 hours. And if it's 2.1 hours, then it's still $18 times 2.1. And when you multiply that out, we have 18, 1, 0, 16, 1, and 3. And we end up with 8, 7, and 3. And 1 behind the decimal, so we move it there. So $37.80. So it works out pretty well overall, right? We can see how much she's making. We can see that that for 3 hours she's going to make $54, and we can see that she is making $37.80 for 2.1 hours. So once you have that multiplier in place, it really allows you to do a lot of extra things, doesn't it? Okay, so that's the idea there behind that one. Let's take a look at activity number 4. This one's called Zeno's Memory Card. It says in the year 2016, 128 gigabytes of portable computer memory costs $32. This will be one of those videos you look back on in probably 2 years and think, that's ridiculous, who would pay that much? Well, that's just what it was in 2016. So the double underline shows that here for 128 gigs of memory is right there, and we're paying $32. Okay, so that's what we have so far. Now let's take a look here. The next question says, turning my page here, it says one set of tick marks has already been shown, already been drawn to show the result of multiplying 128 and 32 each by a half. Alright, so label that memory and there. Okay, now and we want to go here. We're going to do this by half. So to go from here to here by half of that, half of 128 is going to be, in our case here, 64. Alright, and half of 32 would be 16. Alright, and that's our idea so far. Now, the question says on the next page, I'm reading 2 pages at once here. It says next, excuse me, keep multiplying by half and drawing new tick marks until you can no longer clearly label it. So we're going to keep breaking it into half. So half of 64 would be about here, and that'd be 32. Half of 16 would be 8. So multiplying that by a half, right? If we do this in half, we'd have half of this is going to be 16, and half of 8 would be 4. Half of 16 would be 8, and half of 4 would be 2. And half of 8 would be 4, and half of 2 would be 1. Alright, so we're getting down to 4 to 1, and we just keep on going there. And I'm pretty much out of space, right? Now that's a double number line working backwards there, which is convenient, but yet I do tend to run out of space. I probably can't go on too far, can I? That's about as far as I can go. I wouldn't want to go any lower. I could do 2, right? I could squeeze into, well, 2 is the same as a half, and so that's a limitation of the double number line. So let's take a look at what happens if you were to use that same information and try to put that in a table. Okay? When I try to put this in a table, here's what happens. We got the 128, and our multiplier here is times, what do we say? A half. So half of 128 is still 64. Half of 32, multiplier has to be the same on both sides. It's going to be 16. We do a multiplier again of half of that, and we have 8 here, and times half of that, and we're at 32. We do a multiplier again, half of 32 becomes 16, half of 8 becomes 4. And we can continue, 16, 8, 4, 2, and 1. Here we have 4, 2, 1. Half of 1 is a half, and half of a half is a fourth, right? This will be times over here, times 1/2. So a half times a half is 1/4. So the table shows it like that. Seems to be okay if you take a look at it there. And it's the same as a double number line. Alright? So the question really is, did you prefer the double number line or the table for solving the problem, and why? And that's something that it's really, what did you like? What did you notice? You know, what made it more easier for you or more difficult for you? Personally, I like the table one because I can do any amount at any time. I like that I can just change the order up as long as I know my rows are going to be, you know, in alignment and I'm doing them the right way with the same multiplier. I'm creating equivalent fractions, and I don't run out of space. I definitely ran out of space on double number line there. But it's up to you for what you like, and we'll do lots more of these, okay? So Be ready for more. So in summary today, what we have is we would say that finding a row containing a 1 is often a good way to work with tables of equivalent ratios. Once you can find that 1, that rate, it helps you solve a lot of things, doesn't it? So here's two examples as a way of looking at it. If I have, the price of 4 pounds of granola is $5, at that rate, what would the price of 62 pounds be? I could keep multiplying 4, 8, 16, 32, 64, 62 until I figured out how to get to 62 pounds, right? Something along those lines, and figure that part out. And this one went up by 2, then they end up subtracting something. This takes a while to do. But if I found that 4 becomes 1 pound, multiplied by 1/4, and I did the same thing here, 5 times 1/4 is 1.25, then I could use this 1 number, this one here, and then go, let's make it into a 62, do the same thing here, and find a solution. It's just much more efficient when we can get one of the rows to have a 1 there. Okay? And remember, in case you're forgetting here, that dividing by a whole number is the same as multiplying by a unit fraction, right? So divide by 4 or multiply it by 1/4 is the same thing. So don't forget about that as you work through these next problems. Okay, we're going to pause there, give you a moment to work on your homework, and we'll come back and check it together in a minute. Okay, here we go. Time to work on our homework for lesson 12. It says Priya collected 2,400 grams of pennies in a fundraiser. Each penny has a mass of 2.5 grams. So one penny has a mass of 2.5 grams. How much money did she raise? Okay, so here's the information that we're provided with. We know that one penny has a mass of 2.5 grams. We know that in total she has 2,400 grams, and we're wondering how many pennies did she end up collecting to get that mass, and then turn that penny into the actual money that she raised. Okay, so I don't see a quick way to go 2.5 to 2,400. Okay, just not something I noticed there. What I do notice is this. I know I can get 2.5. When I think about 2.5, I'm thinking about 2.5 times 2 can get me to the number 5, right? 5, 0. I like tens if I can get there. If I multiply by 2 more, 5 times 2 can get me to 10. So in terms of a multiplier, if I multiply 2.5 times 4, I end up with the number 10. Okay? So 1 times 4 will give me 4 pennies. So 4 pennies has a mass of 10 grams. The reason I like 10 is because I could pretty much go from 10 all the way down to there, couldn't I? Is that possible? Sure it is, right? I mean, think about it. 10 times what number gets you to 2,400? 2,400. Well, 10 times 240. And I'll show you here just to make sure we got it. We have 0, another 0, and a 4 and a 2. So 10 times 240 can get you 2,400. So I can do the same thing here. 4 times the same multiplier times 240. And we'll do it here. 4 times 240 is 0. 16 carry the 1, 8, and 9. I have 960 pennies. Now remember, it wants to know how much money she raised. She did not raise $960. These are pennies, and a penny is only worth a cent, which means in total she raised $9.60. Okay? So that's one way of doing that table. You might have done it a different way. Again, the goal is to get a 1, and because we were looking at this one, could you have turned that into a 1 of some sort? Yeah, you could have. There are other ways of looking at it. It just, just changes the game a little bit depending on what numbers you use first and what you see. So that's just one way of doing it. That's just the way I did it. But if you had a different option, different way of doing it, great. Just explain your answer. Number 2. Kieran reads 5 pages in 20 minutes. Here's 5 pages in 20 minutes. He spends the same amount of time per page. How long will it take him to read 11 pages? If you get stuck, consider using the table. Okay, let's use a table because it's here. So to go from 5 to 1, that's going to be by multiplying by the reciprocal times 1/5. So to go 20 to this missing thing, we would multiply by 1/5. Well, 20 times 1/5 is 20 divided by 5, which is 4. Okay, we're good there. Now in this case, the multiplier here is 1 times 11. So to go 1 times 11, I would then go 4 times 11, and 4 times 11 is 44. Again, what's interesting about this way of doing it with these columns is the multiplier here and here can be different. The multiplier between rows, though, is what has to be the same. That's what's critical. You can change these multipliers to do whatever you want to do. If I want to make it times 50, that's fine. But I have to do the same to both numbers in order to make an equivalent ratio. All right. In our next question, it says that May is making personal pizzas. Way to go. For 4 pizzas, she uses 10 ounces of cheese. 4 pizzas, 10 ounces of cheese. Let's take a look at the table on the next page. There it is. 4 pizzas and 10 ounces of cheese. How much cheese does she use per pizza? Which means we want to know for 1 pizza. So how much cheese per pizza? Because it's a per pizza is the 1. So to go from 4 to 1, what are we doing? We are multiplying by the reciprocal, or dividing by the actual number, 4 divided by 4, which means I will do 10 times 1/4. 10 times a fourth can be written as 10 over 4. And that works there. 4 goes into 10 2 times, and it leaves me with 2 left over, 2 2/4, which is 2.5. And I could leave it as 2.5, I could leave it as 2.5, whatever you wanted to do, right? If you like decimals, you could make it 2.5, you could leave it as 2.5, not a problem. That's what we know so far. Cool, so that's the first part. So how much is per pizza? We would say 2.5 ounces per pizza. At this rate, how much cheese will she need to make 15 pizzas? Well, she uses 2.5 for 1. If she's making 15, then we're going to multiply that out there. And we have 5, 2, 10, 11, 12, 0. We have 5, and 1 times 2 is 2. So we add those up. We have 1 behind the decimal. So boop, put that right there. And we have 37.5. Okay, so we have 37.5 something or other, right? I was talking, not thinking so much. So at that rate, how much cheese will she need to make 15 pizzas? All right, so double checking here. So to make 15 pizzas, this becomes 15. So multiply by 15. So 2.5 times 15 is going to give us 37.5 ounces of cheese to make 15 pizzas there, because our multiplier has to stay the same. All right. Number 4. Number 4 is a kind of a different problem. Okay, your teacher may have said to skip this one, not sure. Just takes a few more steps than normal. All right. Let's take a look here. Claire is paid $90 for 5 hours of work. So if I set this up, I would say she has $90 for 5 hours of work, something like that. Okay. At this rate, how many seconds does it take her to earn 25 cents? So notice that we're going to turn $90 in 5 hours into a number of cents. We're going to turn it into 25 cents and some number of seconds. That's my goal. Few things kind of that make this problem more challenging. I start with dollars and I'm turning it into 25 cents. So that's different. I am starting here with hours and I'm turning into seconds. So this is not just a straightforward kind of problem where you might see it right away. This is a more challenging problem. Okay, so if you got stuck on this one, that's okay. Let's see if we can walk through this together, all right? So to break this apart, we would say that first we had $90 in 5 hours. So what's good to do is to turn this into how many dollars is that for 1 hour. Let's get that 1. That's what we did a lot today. So 90 divided by 5 is going to tell me that my unit rate is going to be $18 per hour. Okay, that's not too bad, right? Now, in terms of hours, I know that there are 60 minutes in an hour and there are 60 seconds in a minute, which mean that in total there are, I'm going to keep this $18 here, there are 3,600 seconds in an hour. So you're making $18 in 3,600 seconds. Okay, we're getting closer. We at least have the seconds on the bottom, but we're not to that magical 25 cents yet. All right. So what do we know next? Well, we know that we want to, at this rate, we could say this. Let's see how much money she's making in, well, let's do this. We know we got to get to 25 cents, right? So let's turn this into a number that I like. Before I get to 25 cents, let's try to get this to $1. So to get 18 to $1, we do it divided by 18, right? So what is 1 divided by 18? Or sorry, what is 3,600 divided by 18? 3,600 divided by 18, oops, is going to be 200. So $1 divided by 2, so we have $1. You make $1 every 200 seconds so far. Now we're getting closer to 25 cents? Sure, because 25 cents, we get 25 cents here. To go from $1 to 25 cents is what? Divided by 4. Taking $1 divided by 4. 200 divided by 4 is going to be what? 50. So, long story, it takes 50 seconds to make 25 cents. That's a very long, complicated problem, but it is possible to do. Okay, so for number 5 here, it says, a car that travels 20 miles in half an hour at constant speed is traveling the same speed as a car that travels 30 miles in 3/4 of an hour at a constant speed. Explain or show why that is. Okay, so let's think of it this way. You have car number 1 who goes 20 miles, and they do that in half of an hour, right? Which means that in a full hour, this is their speed, and this is their time. In a full hour, we'd be multiplying by 2, right? Times 2 to get to a full hour of 1. So 20 times 2 is going to be 40. So it tells us that in that first car, they're going 40 miles in 1 hour. In the second car, what we see is that it's going, for speed and time, that it's going 30 miles in 3/4 of an hour. Again, to get that to a 1, right? We want to make this a unit rate of 1, we'd multiply by 4 over 3. So 30 times 4 over 3, 30 over 3 is 10, and 10 times 4 is 40. So we end up with the same rate, okay? And we can see that happening there. So they both have 40 over 1, and that's what we do. We just find a common thing here, we find a common time, and by doing that we can then check and verify, are the speeds the same? And indeed they actually are. Alright, number 6, our next one. It says Lynn makes her favorite juice by mixing cranberry juice with apple juice in the ratios shown on the double number line, 9 to 21. Complete the double number line, complete the diagram to show smaller or larger batches that would taste the same as Lynn's favorite blend. Okay, so in this case here we see that we have 1, 2, 3. This is our third batch, right? This is our third batch, and at least, well, if we think about batches, I guess in that way, it doesn't have to be batches, but the ratio is, this is the third one in the ratio number line, which means that if I take 9 and I divide it by 3, that'll get me to the place I need to be right here. 9 divided by 3 is 3, and it shows me that on this double number line I'm counting by 3's essentially. 3, 6, 9, 12, and 15. For 21, I want to do the same thing. If I go divide by 3 this way, divided by 3 gives me a 7 right there. And then I can see I'm counting by 7, 7, 14, 21, 28, and 35. Okay? So it just helps me looking at one, helps me figure out what I'm going to do to the others. And then from there, I know that I'm going times 2, times 2, times 4, times 4, times 5, times 5, and so on. All right. And our last one of the day, it says that each of these is a pair of equivalent ratios, which means they're already telling us they're equal. Explain why. So you're going to want to explain why or draw a representation to show why. So I'm going to kind of mark it through here how to do this, but you have to do the explanation for your homework, I'm sure. So what I notice here is we have 600 and 450, okay, and we have 60 and 45. So it looks a little bit like this. Here's 600 and 450. This is a table, right? And then we have 60 and 45. So to go from 600 to 60 is doing what? multiplying by 1/10 or dividing by 10. Is the same thing happening here? Yes, it is. You can prove that they are equivalent by doing just that. All right, are there some more? There sure are. Let's look on the back side. On my paper, at least. So here we have 60 and 45. So let's think about a table here. I could do 60 and 45. Then I can do a 4 and a 3. Now that tells me it's equivalent. It's just hard to see if they really are or not, right? I don't know. So let's think about this. If I multiply this by 5 times 5 and multiply this one times 5, I'd end up with 20 and 15. Now those numbers are a little more similar in some ways to these than what 4 and 3 looked like initially. Because I can see that with a 20, if I multiply 20 by 3, I end up back at 60. And if I multiply this by 3, I'm at 45. And that's where I started. So we can show that, yep, indeed, finding something in common helps me figure out that those are equivalent. Now the next one is 600 and 450. Is that really any different? Well, let's see. Here's 600, here's 450. I'm going to use the same table because to go from here to here it's times 10, and this is times 10, and I already have the 4 and 3 in the table, so I'm just adding on to that. So yep, that's how that works. That's it for today. Have a great day, and we will see you next time.